Okay, let's start then. Intermolecular interactions we were seeing super well. We were seeing then p-stacking, and we had these interactions in the DNA of the yin monothread of the DNA, and how in the monothread a base interacts with the other, now the biomolecules. It is necessary that you know them because there are several drugs that we are going to see that act in the genetic material or in enzymes, etc. And in the case of the genetic material, something very particular happens. Let's see first, remember the names, which is puric, which is pyrim. Short-term memory, the one above the upper cycle, is a pyrimidinica-based type cycle. It is a pyrimidinica. And the one below is a purine. Then we have that among them, the cycles are establishing a p-stacking type interaction. And that we had already said we had a p-stacking type interaction, therefore, a strategy to create an anti-tumor drug. What would it be? If we have that these two bases have to be like this, and this piling between the bases is formed, what happens if we make a molecule that is flat enough that it can be inserted, slide through the bases, and disturb these interactions? Exactly, very well. We could then create a molecule that is inserted through the bases. Then that would be an anti-cancer molecule. How does selective work? It attacks the same as healthy cells. But where is the difference that an anti-cancer molecule is going to be more toxic, or should be in the tumor cell, because the tumor cell is being replicated faster and structurally for this to work, there has to be a minimum of molecular surface, so that a good intercalating agent fulfills its mission. It has to have a flat surface, enough extensive that it allows you to make good p-stacking interactions and others. If the molecule is very small, a pure ring of benzene will not. Well, that is to gradually deliver the concepts of pharmacophores. Here, we have another example that no longer has anything to do with genetic material, totally new. And what can you tell me about this type of structures? Like this formed by carbon atoms, this is I think it was the name on the tip, this is a fullerene. A fullerene is a molecule formed only by carbon. It is a cycled structure, and with the double link that is here, we have this representation that seems to be a ball, a sphere, but they are rings that are interconnected, and we have another molecule that adheres to this structure here, also formed by aromatic rings that adheres perfectly. And the coupling is only by p-stacking type interactions. For what could something like this be useful? Well, it could be useful. The application of this, which is is for exact transport of drugs. We could, with nanotechnology of this type, transpose a drug that is 12, that has good interactions and would serve to arrive more selectively, for example, tumor. Then this type of interaction is used today to adhere one surface to the other. And now it says here, other interactions. They follow in importance, other interactions. No longer is p-stacking the ionic interactions of Saline bridge formation, for example, often reinforced by hydrogen bridge. And in this image, we have a double interaction that is taking place between an anionic residue and a cationic residue. Let's suppose that the carboxylate came from an amino acid residue. What were the two amino acid at amino acid residue of acid type, the vitamin acid and the aspartate. Very well then, it could be if it comes from amino acids glutamate and aspartate. If this comes from the amino acid of the ammonia, what amino acid would it be? And here there is only alternative for it to be from the perfect if lysine would be of lysine. Now, obviously, in reality, it will happen that one fragment of the drug and the other of the protein, and then ask what is happening here. The ionic interaction between these two fragments is at a greater or lesser distance than the interaction of hydrogen bridge, because here there are two, and on the other hand, ionic interaction, excuse me, less or greater than the hydrogen bridges. The hydrogen bridge in general, since here, this is super close, is 2 angstroms, 2 angstroms and a half here. I think we are closer to the 2 fits perfectly well. The hydrogen bridge is measured from the oxygen nucleus to the proton. On the other hand, the ionic interaction is measured from the oxygen nucleus to the nitrogen. Then where is more distance in the ionic interaction? The ionic interaction in this case also happens with the other oxygen and nitrogen. Then the distance of the ionic interaction is greater than the distance of the hydrogen bridge. That is relevant when making drug design because one can play with the distances when one sees the receptor. Ask what were the other basic amino acids. They do not have this free functional group like a lysine, the other basics, so that they can remember the basic amino acids. What were the other basic amino acids? Very well then. We would have arginine and but the arginine was not the one that the one that had the cyclid already had a guanine group, and the other one was C. We lack one that had the but the polypyrrolidine or histidine. And histidine was the histidine, and that was the other basic. Clear. And therefore the residue is actually hydrophobic. Then we have to have arginine and histidine lysine, so that they gradually go by passive diffusion. With intermittent reinforcement, we are going to try to learn the residues of the amino. It is very important which of all those can be neutral or charged according to the condition. Average AF7, but the lysine. To see what happens here if the Pegasus 7 is here. Therefore, histidine can be positive or neutral, and that makes it so relevant in catalytic sites of enzymes. Very well, here next to it, there was only another image that showed an interaction, as we can see here, of hydrogen bridge between the carbonyl of a protein, and of course not certain a group, in this case, not certain positive of, for example, a drug that is from a drug, and we are going to have that the interaction of hydrogen bridge can occur, but also the interaction between the charge and the oxygen would be interaction of the type John dipolo, that John positive dipole of the oxygen. Then we would also have a double interaction, but this is not a saline bridge, so be careful with that. A style where well, it says here other interactions, and the interaction of type pication is mentioned here. So this one that we are seeing here is the interaction pication. Example, an aromatic residue. Let's imagine that this is part of the protein if it is part of the protein. I want you to name me which are the amino acid residues that have penicillin and phenylalanine. Very well. Which one else already perfect the tyrosine? Very well. And which one else another that has benzene in the structure? Not necessarily. The free benzene can be fused to something. There would be one there aromatic. Still okay. Those two are super important. Phenylalanine, tyrosine, and a third is missing. What happens is that the histidine is a ring of 5, not 6. And I say of benzene derivatives. Okay. Very well, the crypto is perfect. Then there we have residues that have a benzene aromatic ring. What is happening is an attraction between the benzene new VP and the positive nitrogen atom. The attraction is not with what? The protons, but with the nitrogen. That is the strong interaction here at a distance that can reach up to about 4 angstrom. These interactions are at great distance and are weaker than the hydrogen bridge interactions. And there the question is, what would happen with an interaction pKp anion? Very well, then we are going to say that an interaction of type anion pi would actually be a repulsive interaction, but attractive pication. So there is no anion-anion interaction that is attractive. Well, all this is going to serve then for the design of drugs, because one of the parts of this course, one of the objectives is that they are able to design drugs with qualitative tools, without even needing to resort to great technological advances that we are going to occupy you. Will be able to design very well. And finally, the last interaction that we lacked to see the hydrogen bridge. The hydrogen bridge, we are going to make a small tour. This interaction is very interesting. It is an interaction that sometimes happens at the top in the design of drugs, since usually the allergens, when one thinks about them, only thinks about the physical chemical contribution that they make to the molecule. And here I am going to ask you a question in general already. Have fluor, chloride, bromine, and iodine already in general? Well, I lack iodine there in general fluorochloride. Bromine and iodine, what contribution do they make to the molecule? Lipophilia or hydrophilia? Perfect. Then, in general, they increase the log P of the molecule, an increase in the lipophilia. Then, in those terms, one thinks of molecules that make it more lipophilic already okay. But here, it says that a century and a half ago, the formation of a complex between iodine and ammonia was described. That is, this is iodine molecular interacting favorably with ammonia. Remember that the ammonia has a geometry. Of what type is the geometry electronically? If it is a tetrahedron and molecularly pyramid, then a strong frontal interaction we have there. And well, the iodine, the certain molecular iodine, would have 2, 4, 6, 8, knitting 2 electrons in the valence layer. And of no link, then the question that arises is how a complex was formed. That is, this was favorable and attractive between a molecule full of electrons and the nitrogen, with electrons also to the shop. Here it says chlorine and bromine, with amines. So it is exactly the same principle. Yes, okay, of course. Here also already chlorine and bromine, with amines, is the same. only that a proton is replaced by an air in the years of 1962. Hassel published a work in which he described in solid phase what is called for the first time in that year as the molecular halogen bridge recently in 1962, which is more or less the date when it begins to be spoken for the first time. That is invented what is called the Cursor studies. So in parallel, more or less to that date, the Cursor issue was happening that we are also going to see. The continuation, well, it says, Hassel obtained the Nobel Prize in Chemistry for its contributions to the concept of conformation and its application in chemistry. However, its conference was about halogen bridges. Many times it happens that people discover something, but they do not win the Nobel Prize for what they discovered, as they need to win the Nobel Prize for why they won the Nobel Prize. Relativity, remember, it was due to the photoelectric effect, and relativity came later or in parallel to that, but the Nobel Prize was due to the photoelectric effect, because to be something empirically demonstrable, not a theoretical speculation, despite the fact that later, the experimental theory was also demonstrated several. It was observed in the collection of organic crystalline structures, Cambridge Crystallographic Data Center, that the interaction angle carbon yield oxygen is close to 180, and some distances are usually shorter than the sum of the van der Waals radii. Let's go there. Sum of the van der Waals radii is when one has an atom A, an atom A, an atom B, an atom A, and an atom B here next to it. If they are tangential, the atom A with the atom B, the sum of the always measures from the core, from the center, that would be the distance, and this distance would be equal to the radius of A plus the radius of B. And if here it is being said that the oxygen yield interaction is shorter than the radius of A and the radius of B, which means that they are overlapping, and therefore that there is a strong attractive interaction. And we have then that when there is carbon yield oxygen, the following happens: the electronic pair of oxygen has to be at 180 degrees with respect to carbon yield. Here is where there has to be an angle of 180 degrees. 180 degrees. Then the angle of 180 is between carbon yield and the electronic pair of that oxygen. Then it is the same as the oxygen is located. Not true, because the electronic pair, at what angle is it with respect to the double link? If it was a carbon yield, 120, very well. Then it does not give the same angle. Here we have an angle of approximately 120. Then it does not give the same angular disposition. Well, again, here the question is okay. This interaction is because it is from the explanation to that. We have it in a quantum phenomenon. Then we are going to move forward to give the final explanation of since the 90s, the concept of crystalline engineering, halogen bridge, has been used, for example, in the design of solid phases with conductive or semiconductor characteristics. In other words, the halogen bridge allows the flow of electrons through the molecular framework. And here we have a concrete example. This is a system of type conductor crystal, and says there are superconductive crystal, therefore allows the flow of electrons from one side to the other of the other. Molecular, quite easily remember that the superconductors, what is the characteristic? That they do not offer resistance, and therefore the energy is practically not lost. It is not lost in the form of heat or noise. They have not heard the tension towers that sound. When the energy dissipates, then there is a loss in heat or noise here. No loss happens there. Electrons flow super well. And what we have there is the following: a gold atom connected to nitrile group. And so, 4 times. And that nitrile group, okay, nitrogen, which would be this blue atom, is, in turn, doing favorable interactions, as we can see here. The three-dimensionality of the crystal is doing a favorable interaction with iodo atom. So then a iodo atom comes here, connected in turn to the aromatic ring. There is then happening the interaction of halogen bridge. And that allows the jump of electrons from one place to another. Well, at the beginning, when you just start to see this type of interactions, it is very rare, because it should not be as certain that a nitrogen atom with an electronic pair has some B type of favorable attraction with a rich iodo atom in electrons. The answer where it is in the halogen, okay. The answer is always in the halogen. We go there here. This is already one of the last introductory examples. How is this ring called this heterocyclic? What is the name of this heterocyclic? Exactly, pyridine. And pyridine, remember that it has. And here we have again that this pyridine is interacting with a iodo atom that, well, when what has been seen that the halogen bridge is strong, when in the aromatic ring, in this case, in the benzene, that is connected to the iodo atom, we have this, that the fluor atoms play a role. Electrolytes or electric attractors are very good. They are strong electric attractors. All these are old. Strong electric attractors. As is, the iodo becomes quite deficient in charge by the effect of the fluor, even without the fluor. The halogen bridge works the same, but it is enhanced when in the aromatic ring there are systems. Electroattractors, the interaction becomes stronger. Is there any protein that has fluor? Chlorobromo or iodo? No, it is not true. There is no halogen in the protein. Therefore, it will always be in the drug. That is an image only of the liquid crystal. And to be able to understand the interaction, remember this: the halogens are small or large atoms, and large except the fluor, because the fluor is the only atom in the periodic table that is similar to hydrogen. Okay then, fluor and hydrogen are of similar size. This is expressed in angstrom, where an angstrom, remember that it is equal to 10 radians. Then fluor and hydrogen are very compact, very similar in similar size, who therefore participate in the halogen bridge, chlorobromo and iodo, okay, which is the largest iodo, of course. This giant, okay. We can do it like this. Then the bromo would follow in size, and finally, the chlorine is the smallest, okay. Although very similar to the bromo, there are also relatively large atoms such as sulfur, but later they are much smaller, oxygen and carbon. When an atom is large, it can experience larger size. We can have greater radial polarization. We have greater radial polarization means that the electrons can move on the surface of the halogen from one place to another very easily. The electrons move, that is. We are going to say that the halogens are soft atoms. The electrons can move, they can migrate, except in the floor is a hard atom. The electrons are not going to move in the floor because it is very electronegative, and therefore, if radial polarization occurs, we are going to have to. And that we can illustrate in a graphic way in this way, that if a halogen is not connected to an aromatic ring, then, for example, the iodo we know that it is large, then the electrons experience radial polarization and move backwards of the molecules as they are collected, and we have that on the surface. The electrons begin to go backwards, and there is a space here where there are no electrons, and we are going to put a name to that space there, where there are no electrons, is called sigma hole. And that is electropositive, that is delta plus, and the electrons are collected, so to speak. Backwards here in a radial way, we have a delta minus. We have radial polarization. The atom is so large that it is a dipole positive charge and negative charge in the same atom. Question here, you believe, which is the one that polarizes? Exactly, the largest one is more polarized, so the halogen bridges with iodo are quite intense. But why don't we see so many drug iodine? Because it is not so common. If this interaction is going to be strong favorable, there is a limitation to insert a lot of iodine in a drug. It can be done, but at the level of the patient, of the person who could go through with very iodine molecules. And of course, allergenic, that there is a lot of iodo. The iodo could generate rejection problems. It is allergenic. And that is why in that case, we resort to chloro or bromo, any of the two. We will resort to chloro or to bromo, which are very similar in size. So there is a small limitation. I do not say that it cannot be done, but it is a limit. I even modify this at will. Well, here we have 3 molecules where we can see in this study reported in 2009, where we can now see at the computational level what happens with the electrons on the surface. That is, this is a map of molecular electrostatic potential, or potential electrostatic map. And in the first case here in red, if you look, we see the structure. We have that there is a benzene connected with a CH2, then comes an oxygen, and then comes all this aromatic ring. And here below it has a chlorine. So here we have a chlorine atom. This other one has bromose, and the latter has iodo then. Here we can see, okay, this would be the chlorine. Here is the chlorine, the bromine. Here are the bromine. And finally this iodo, this sphere, here and there, you can see the radial polarization that it experiences. Then what does green mean? It means that there is radial polarization. Okay, this is the positive side. Has a load deficiency, is delta plus, but who has a more positive sigma hole? The bromine wins here. We have the other sigma hole, and finally the iodo. Here it is super blue, right? Not only then down, we improve that it is more positive. But what other small factor with respect to the sigma hole itself? The sigma hole is the same in the 3 cases where it is larger in the iodo. It is not true, and the sigma hole has a larger size. It is more positive, and that would explain then why this can interact favorably without an atom rich in electrons. What a rich thing in electrons we have in very well. A carbon dioxide or a nitrogen could also come from the protein as long as B. In some way the electronic pair is more or less oriented. They cannot be oriented. The proton is understood. You have to give the negative part oriented towards the sigma hole. So make good interaction. And also the following can happen, for example, in the case of the... And here, it has also been seen that sometimes there is a bridge of halogen, and simultaneously a hydrogen bridge, as how it can happen simultaneously in the same atom. That excellent. Very well, the red zone exactly here. In the red zone, we can have a hydrogen bridges. Then, an oxygen could come connected to the rest of the structure, and there hydrogen bridge, and at the same time, a bridge of halogen. That is, it is very versatile to have a halogen structure perfect. Having said that, then it is quite understandable now. Some concrete example. More show here the small calculations, and with this, you will never forget here. There is a Benson Ebert. It is like this. It is not true. The plane of the Pizarra cases this sigma, and what happens? So be very careful. The flow does not make a bridge of halogen. It is 100% negative because there are both the others. If we have positive, and this giant here is not true positive, then chlorobromo go the sigma hole and the radial polarization. But flow can only make a hydrogen bridge. Then fluor only makes a hydrogen bridge. The others can do both things. Here, there are other molecules where again you are going to identify easy and fast. Not true. The halogen could here, for example. The halogen is this, and this. Here is probably an oxygen. Not true then. This would be the halogen. Immediately here one says, there is the sigma. Striking, immediately, we know that there is the halogen. And if it seems edible, very well, it's an example. Says an agent who interacts with the factor of coagulation 10, that is, this molecule was designed as an anticoagulant agent, inhibits the coagulation cascade by joining the 10 protein of the blood, coagulation, cascade, question if E. I think it is unlikely here between the chlorine and the oxygen that there is an interaction. If it could happen exactly, good observation, it could be, if we count there to see, let's say 1, 2, 3, 4, 5, and 6. And it could be happening, of course, if an interaction there. The truth is that it could turn because we do not know the conformation that this has in space, but there is the probability that it is frozen intermolecularly. It could be that it is relevant about when one designs a drug. Once you do not want, that one wants the proton to interact with the proton, not internally. Therefore, sometimes it is not good that because we could replace the NH by a simple carbon. It is not true, or we would have to rent it for a methyl. It could be rented with a methyl or an ester. That is more reliable, and ester would break relatively easily. What is the name of this ring? Benzothiophane. Okay then. And we have there a group X that says here, when X is chlorine or bromine, it says the maximum power is achieved if you have chlorine or bromine here in X, and if you replace any other thing, the activity decreases. What does that mean? That is making an halogen bridge. Because fluorine does not serve chlorine or bromine here, there is another derivative similar to the previous one. Also, doing the interaction, then ask here, we have 3 halogens. They are already chlorine. This one, the one above, and the one above, okay. Then what is the halogen bridge, for example, here? With which residues? We already have interaction with alanine tyrosine and valine interaction with alanine interaction. With tyrosine interaction with valine, with which is more likely based on what we explained at the beginning of the angle that a halogen bridge is being carried out. The angle for the halogen bridge did not have to be How much 120, 180 then? With the tyrosine with that, is the straight line here. The image then, there we have 180 degrees. And therefore, there we have the halogen bridge. Second question, with what thing of the tyrosine is doing the interaction? Because here is only the code. That is what you would expect. That is happening here, and there are two possible answers already. Very well, there are two possible answers. And I am going to mark it if, because it turns out that a possibility is that it is the residue of the tyrosine that is generating the interaction. Which residue of the tyrosine? Oh, that is is the alcohol of the tyrosine that is doing the interaction. But it has been seen, and that halogens have a greater degree of penetration. It is called in the protein, that is, it is very common that the halogen bridge occurs with carbon dioxide, or NHA. Carbon dioxide, or NH of the protein, is very common, that type of interaction. Therefore, it is likely that the halogen, as it enters more in the protein, so to speak, and in reality, maybe instead of doing it with the O, it is doing it with the carbon dioxide of the backbone of the peptide bond, that is, with the PAO, carbon dioxide of the tyrosine. Then the other possibility is that the carbon dioxide, you see, that it is interacting what thing? The oxygen, of course, of the carbon dioxide. Then the tyrosine makes the interaction with the carbon dioxide of the backbone. That is very common in halogen bridge. It is like that the halogen reaches more inside, so to speak, within the protein. It has more facility because it has greater radius. Then it enters more. And therefore, the residues would rather be a disturbance, and the halogen reaches the very backbone. Now, what implications does that have, for example, when one is designing a drug? I am going to give you a concrete example, an anti-neoplastic drug. One of the problems of the anti-neoplastic drugs is that there is resistance because the cells mutate the proteins. I do not know. Other neoplastic cells mutate, and for example, if the tyrosine mutates, one says it will interaction. When there's a halogen bridge, many times it is not lost because the exact backbone will not disappear. It gives the same that the residue you have here, if the interaction, the halogen bridge will not be lost. But if you had a hydrogen bridge, it may be lost. Then the halogen bridges are particularly useful when one is treating pathologies that offer resistance by mutations called anti-neoplastic, antiviral, and in general, any cytotoxic, antibacterial, antiparasitic, antifungal agent. That type of situation is very, very relevant. The halogen bridge, the molecule, becomes invulnerable to the mutations of the protein. Thanks for the observation I have been forgetting to mention, and that, of course, if those two extra interactions, and it is less likely now, but if it could be that the NH is touching the negative part, or well, if it is that oxygen also looks here, hole of the sigma hole is large, the halogen is large, then it could be more than an oxygen at angle to be interacting. But these interactions would be weaker because they are not at 180 degrees. Then remember the halogen is large. The sigma hole is large. Then sometimes it happens that more than one interaction can happen, but one of them is strong and the other's weaker. Contacts perfect. Let's go down here now. Second question. What is this then? Here again, we have our halogen interacting with what was this? Is very good sulfuric acid. Therefore here, I have no doubt because look at what happened. That interesting, yes, exactly. And the other, instead of saying, it is perfect, cysteine and methionine, for some enzymatic process, they were interconnect very well. And the question is, what is this? Because here in the middle, this is pointing to the link. Then N as a ratio, and it is already a bridge, and in reality, it is clear that what we are going to explain now gives the impression that it was the link. But in reality, that is a summary of saying that some electronic pair of sulfur is actually the one that is doing the interaction. So be careful, it is not that it is the link in itself, but that it is actually some electronic pair of sulfur, or both, that are doing the interaction will be in. Because the sulfur is electronegative, and the halogen does not have there the sigma hole, electropositive. Then there is the sigma hole, electropositive question, and the sulfur can also be an acceptor of halogen bridge. And the sulfur is still big, but not much more. Careful, the sulfur does not have radial polarization, as the halogen throw the electrons back to generate an artificial sigma hole. It will not happen, and so much careful. Of course, exactly. It is much more exact in chemical terms. It is harder. It is less polarizable. Very well, and finally, here we have the last halogen. So here this would be the chlorine interacting with another tyrosine. Same situation. Maybe the O, as it is not described. Maybe the O, or the carbonyl, or even the nitrogen of the peptidic link already. But it is less likely that it is always a carbonyl or a residue. Second example. And now here, we begin to deliver some additional quantitative value. They say this problem, the replacement for methyl of the bromine that is there in the molecule that is found at 3 angstroms of the carbon dioxide of F. That is what is F at the level of amino acids. Phenylalanine very well results in a decrease in pKi for the monophosphate dimidine. Quinine, an enzymatic inhibitor, an antiviral in this case, and we have that the distance here is what I am interested in, that we highlight more or less than hydrogen bridges. More true they can occur, because a halogen is larger, and therefore, how this nucleus the distance is greater. Where is the interaction then? That interaction, that here, which ones we are going to maximize? Find the halogen bridge, a challenge. Of course, because it was said that it was the F36, and then it is the residue, or it is the residue. Back very well then. What you see, there is the carbonyl of the backbone that is being shown. There is the carbonyl of the backbone, and the halogen, here is this, would be the bromine. And then this would be the atom of bro, and the interaction as we see. There is, with the electronic pair on the side of the carbonyl, with the sigma hole, does not have a perfect angle of 180, but there is contact and the residue for where it is for anywhere, or the residue of A. Storm, the halogen managed to get more into the protein. Well, that interaction then is relevant. We go to the next problem. An inhibitor of transcriptase enzyme reverses another antiviral, in this case. And we have the following. It says that the inhibition, the activity of these inhibitors, should be the formation of halogen bridges are looking for antiviral enzymatic inhibitors with halogen bridges. Yes, because it turns out that the reverse transcriptase, and that is published in scientific paper, the biological entity with the highest mutation rate that exists on the planet is the enzyme. That mutates faster at the biological level. And then we have to hear the interaction is shown first. We see the molecular structure we have here, the iodine atom, and the question first is the presence of these two oxygens favors or worsens the halogen bridge very well. Then favors the electric attractor. The electric attractor increases the delta plus of the halogen ion. And here it is happening. Here is the halogen, the iodine. At 344, angstrom is interacting with very good backbone carbon dioxide then. If it is there now, we see that it is doing a double interaction as it is, and down here then very well. That is the NH. Remember that the NH is available as it was called, that the proton. Because it asks here, the proton looks at the halogen transoid. The proton, so be careful, if the proton stays forward, it would disturb, and the proton cannot be moved. The transoid, the proton is backwards then. One says, and how can it be, if because the nitrogen has an electronic pair? But this interaction is poor. This is not the best electronic pair is from the exact location. Then, this interaction is not the most relevant. The above is the most relevant. The second thing that catches the attention is that although it is true, is with a carbonyl and with an amino but of different amino acids, it is not without the two of the same amino acid, but of different amino acids. Then he reached the protein in depth okay, and the residues come out because the iodine approaches directly to the backbone 3.88 and 3.4 angstrom. It can arrive, I think I gave the value 4 angstrom there. We see that if, for example, it is close to 4 angstrom from a distance, then it is angstrom, and that is angstrom. Question: what would happen if you replace the iodine with? The affinity would even go down because there would be, for example, with this oxygen, it may even generate a repulsion, although of course being smaller capable that it does not even reach us so close to the residues. In this case, precisely since this is mutant, it helps a lot to have a halogen there that is derived from thyroid enzyme polyiodine. We have here, technically speaking, these 4 molecules are amino acids. Of course, they are amino acids, but not structural amino acids of protein. They are amino acids. They are hormones, it says here. Then we are going to mark. So they are amino acids. And the last one says that it does not have activity. The third one says here, almost no activity, halogen, within the structure, okay. Then, as we increase the affinity of the compound by the target increases, is an example that only shows how polyly iodine something generates a good Here is thyroid hormone, and there you can see the pinch. Here I have the electronic pair then again. It says phenylalanine. Phenylalanine has a benzene. Again, it is the oxygen backbone. The electronic pair is at 3.05 angstrom of the sigma joule. The angle is almost 1. It was not for the example. The examples only clear coincided, but it coincided that in this example, it was phenylalanine, but it is not mandatory that it is phenyl. Other carbonyl of the vacuum, 180 angles, then of interaction, is very good interaction. In the second example also there, they have another derivative, very similar, Zami, only that the angle is further away from 180 okay. But again, there will be here the between oxygen and iodine phenylalanine, 121.8 degrees, The electronic pair here pointing to the sigma, joule, and 3.23. We see this last one here, crystalline structure of the kinases complex CDK9 and CDK2 that are stabilized again by halogen bridge. Then again, we have drug here that is imitating in this case, in particular, to what thing this drug would be an imitation of what natural thing. But look at this part here, this is oxygen, oxygen. Then we have that there is hydroxyl, hydroxyl. This here is not true, it is H2O. Then, that has the face of carbohydrates it has. Faces, but it is not carbohydrates itself, but it has a technically for it to be carbohydrates, we need it to have an ethyl function, and it does not exist. And then, here we have the heterocyclic connected. This is very similar to a nuclear. Okay, that is the necessary fragments to synthesize genetic DNA material, that is a carbohydrate connected to a nitrogen base, but this is not a nitrogen base. That the heterocyclic is this. Medicinal. There is the famous benzimidazole chlorate. Okay, it's a benzimidazole dichlorate, and they are those. Chloridostat. In this case, come here to show us the great enzymatic affinity of this drug. Here it is, then backbone again. And what happens with this one in blue? Nitrogen. But it will not be the proton comes as it does to us then. Of course, it is like a side contact, so it is also part of the halogen bridge. A triple interaction. That is why it says that they are all halogen bridges. As everything above induces to think that the halogen bridge could be an element in the design of drugs, of course already to see. Before, you see that we leave it there. Small. How much was the average energy of a hydrogen bridge? Exact that average value, because the highest rank good halogen bridge has the same rank as a hydrogen bridge. Then I want you to remember that, and you will not forget the importance of the halogen bridge here. It is hydrogen bridge, oscillates from 0.25 to 40. We said that average value plus the value that is repeated plus is around 5 kilocalories more, as well as halogen bridge, where they have exactly the same rank. Halogen bridge says that it goes from 1 to 40 kilocalories more than. They are practically the same difference when you have a halogen molecule. The pharmacokinetic properties are different from a molecule that is not halogen, which tends to be more hydrosoluble, which molecule is more hydrosoluble, the halogen or the no halogen, nothing exact. So the pharmacokinetic properties change. Very well, it says it's so. Usual energies have similar values. Show the pp interactions, Salini bridges, greater than that, the hydrophobic interactions, and van der Waals contacts. Well, for now, and finalizing the idea, Zeiss in general, I am also, we explain the force of the halogen bridges decreases as C. The radius decreases, and there are no examples that involve and obviously apart from the radius. That also depends on the angle of interaction. There is a concrete example question, the biological activity. We will get these derivatives, the biological activity, when it is greater, when it says 50 or less than This is concentration inhibitory 50 concentration that measures 50% of enzyme activity exact to lower value, greater power. Then we are talking about the most powerful here is very well the one that has Jodo in R5 is more powerful than it would follow without a joke. And then the other two are not true later. They already have values. For example, this one on methyl disappears, something is maintained with hydrogen. It draws attention. It is not true. There is retention of the activity, but already the methyl, because with the methyl, you believe that it is ineratus are very good. Very good question. And which of those four here to go ahead of the Kuzar that we are going to see? Also, which of these four has the largest P and C? We are going to calculate here. Look, let's do the following. And to go P, we are going to calculate that next to the P and C50 and the P and C50 is dimensional. Then help you to calculate quickly the P and C50. That is dimensional, and for that first, all these values taught are here must be expressed as molar, not as micromolar. Because they are as micro certain, as micro then micromolar, you say that value, I take it to molar. And from there, I calculate the P. What is PP? Is less logarithm exact of the IC50. Less logarithm. Then we quickly calculate the values of the most active series. Yes, but if we do a check, for example, in the bottom, this would be the same as saying six minus logarithm of 2.4 necessity. So it was done or not, if 6 minus until a second that I am going to calculate here where I have scientific. Okay, 6 minus parenthesis logarithm already of logarithm of 2.4, and that would give me the below 5.62. The other would be 6 minus logarithm of 13.95, 6 minus logarithm of 59.61, and finally, not true. 6 minus logarithm of 17.5. We are going to calculate those values. Let's see how at the end of the explanation, 6 minus, and there we have. This is 4.86. This is 4.22. And finally, the one above is 4.76. Because there are orders of magnitude, and you have to do the conversion, and I am going to show you now. Because with this, we are going to work in tables of Kuzar. Then the conversion has to be done correctly. PI50 takes up a lot of scientific articles on these topics. And as you can see, the most powerful has the highest P value, the lowest. The most powerful is the last one, is not true. The smallest IC50 exact, or the largest PIC50. So they are inversely proportional. Be careful. And there it is not to annoy and calculate numerically. Whatever we are going to occupy, we are going to work in Kuzar with these values and why. Not true this value 6. We consider the below 2.4 micromolar says, and then we are going to do the calculation here. 2.4 micromolar, well, that is the value, and that is the value of IC50. Then as we wanted the P, we are going to say that IC50 is equal to 2.4 by micro means 10 raised to less than minus 6 molar. And now we calculate less logarithm, which is equal to saying P. Then we would have that the P IC50 is equal to less logarithm of 2.4 by 10 raised to minus 6. Now, yes, it is not true. And there, for logarithmic properties, that properties apply to. In addition to the truth P IC50 is equal to, and there we have the separation, we have this exponent. Exactly 6 minus logarithm of 2.4. Then the explanation came, and that they are going to have to always do what happens if the activity was nanomolar. What happens if it had been 2.4 nanomolar? And therefore, the formula would be 9 minus logarithm of 2.4, and so be careful, because I am going to pass you some tables of some works, and you are going to convert that numerically. Way in here, sometimes mistakes are made. Sometimes the question arises how to convert that we are going to see in the most practical part, and in the past at some point to see if, without the desire to be self-referring, but for I do not know if this will always be here the problem. That you have to be clear. And well, there it is. For example, we are going to any one that has well, we are going to this small table of a work of Kuzar, where we have the activity that is minimally inhibitory concentration. That is, these are antibacterial, and notice that the mic is expressed in micrograms by ml micrograms divided by ml. How do you get to the pain mic mole? Divided by liter. Well, you have to transform from microgram to mole. And how do we do that without the molecular weight of the drug? That is, we had to transform from microgram to ml to mole per liter. And there, it is nice to apply the least logarithm, another example, and to be able to have that value. And then here, seeing this value, you say the highest is the most powerful when you see. What happens if one has another variable, a little more rare, as for a plant that grows, and so that you see that this is not only applied in medical chemistry, but that this can be applied in infinity of things here. Look here, it was seen that the plant grew when it was applied to a certain drug. It is elongated, then millimeters. Not true, we can make the conversion to elongation. Then we have here elongation p, the least logarithm of the phi. Elongation experienced by the stem of the plant. So we can also take this too. How it is called to any variable now, you will not even why you have to calculate because I cannot work directly with the number, because I have to have a logarithmic value that comes from the Heinz equation that we are going to explain later, that shows that the linearity of action of a drug is better explained when the logarithmic scale, that when you do not have logarithmic scale, in other words, with the logarithmic scale, you find a linear equation between the activity and the biological descriptors that explain this activity. We are going to start with what is called free Wilson descriptors that are structural. We are going to start with that, and to finish the idea, here it says. Finally, another one is shown, and help me here to find the halogen bridge. Then there are two superposed drugs here, and it seems to be us. Where is the proline? And then here is the proline, okay. Here is the oxygen, and it is projected very well at 3 point, very well, perfect. Then which drug is better, the pink or white? The pink is. Being halogen bridge, the white does not have here an ethyl, the other has the iodine, and up with the valine, and also very well with the carbonyl, because here is the reservoir, the alkyl chain of the valine. So again, and here what is this? Exactly, this is a hydrogen bridge. Very well, this is from the purple. The two have to see the purple. Of course, here's the proton, and is doing the interaction 2.7. Then see the interactions are at a greater distance, and they are as powerful as well that I already explained. The angular disposition has to be around 180 degrees ideally, and against more angular, it is losing if it is not aligned. The force of the interaction losing it has been seen. Of course, the interaction is stronger if it is linear 180 degrees. The interaction energy is greater than within the range to reach 40 kilocalories. That everything theoretically, yes, but it costs a lot to catch that something has 40. That would be a very but of course in theory, yes, if the conditions were ideal and we would have the maximum energy. Well, the last thing is that it has been seen that sometimes in some crystalline structures, water acts as a bridge. Then what we have here, that which is there, is a molecule of water. And the question is, what is happening here? This was crystallized. This has value when you find it in the crystalline structure of a protein. Here is the halogen with halogen, with whom it is interacting with the oxygen of the water. Therefore, it is the sigma with the electronic pair of the oxygen of a molecule of water. And in turn, what is the G? Molecular of water with the protein can act as a donor or acceptor of the hydrogen bridge, because this is a donor or acceptor of the hydrogen bridge. That is, the water forms interacting a favorable interaction mediated by a bridge of halogen. When this is important in drug design itself, it is not very relevant, except that you find it is a real crystal protein. When one designs it and one puts water so that the interaction is achieved, it is not very credible. It has a lot of margin of error. When one wants to design, one wants the pharmacist to do the interaction. Well, and yes, exactly. It is interesting that there is a whole topic in tropics there. Of course, that is why I tell you that. Molecule of water. How do we know that it is there by crystallography? Because the common sense tells that in reality, it will not want to make a contact with a halogen. But this happens. The question is for how long it happens. If it is crystallized, it means that it is relevant. If it is not crystallized. It is not relevant. How can you get information if this remains or not? Over time with the molecular dynamics calculation. You have to do a molecular dynamics calculation. Is the only way to see if it lasts or not. Over time example. Look, when you make dynamics, you demand that it obviously goes with those. Water. Because one has to simulate the cell, then when one simulates the cell, this happens. And you can find things like this. Here look in this study. And again, it is not to be self-referring, but it is what I have at hand. Here to show you. This was found that this molecule is very good. It has a very favorable pattern of interactions with the protein. And here, our lysines here is the tryptophan phenylalanine. And you tell me first question, what interactions is being done as this functional group is called very well a carboxylate. With the lysines, that interactions are these. Very well. The lysine is positive silene bridge and hydrogen bridge, the sum of all those percentages is the time that lasts through the simulation. That is, if you added all that, almost 100% of the time there is favorable anchor. Ask, what interaction is this? Hydrogen bridge, the arrow based on oxygen, means that the NH polar proton of the tryptophan is making a hydrogen bridge. And what interaction is this? And it is very good. These last two are stacking with phenylalanine, and with phenylalanine they last for 64% of the phi simulation, and it is for a 57 question. The hydroxyl did something through time, not much. It seems that the hydroxyl does nothing okay. But here comes the relevant part, that hydroxyl, that is there, has a tropical role that was discovered when the simulation was made. Without the hydroxyl, one would hope that all this remains the same, because the hydroxyl doing nothing is in contact with the water. But here comes the drama. Look, we take out the hydroxyl and see what happens. Something not very pleasant happened. This is the same, but without the hydroxyl and Bell. Since the hydroxyl is not there, the water invades the cavity, and the water that is being now mediating the interactions you have, but it still maintains them. It is not when the interaction occurs directly. That is the problem. It seems to be that it favors that the water entropically prefers to be on the outside than enter the cavity, because the hydroxyl is polar. Then the interactions of hydrogen bridge with the medium. But when removing it, the water is like it does not have that guardian there, and invades the cavity, and it does not generate this problem that one says, of course, but maybe they still last. But this is less stable than directly with the protein, so that to have it in consideration. And we return here. And with this, we are ending today's session here. It is simply showing the water. What the water does, we go back here. And I do not know why it does not. There we have that the water is the water, as you can see, doing what thing? The hydrogen bridge, okay. And this could also happen because here it says hydrogen bridges. Exactly, very well. With the negative part of the halogen, it is on the side. And you can measured by water. And the last one says here, and why should attention be paid to the halogen bridge? Because the proteins are formed by peptidic links, and the presence of oxygen atoms is common. That is, the entire backbone is full of oxygen. Those that can be used to interactions of the halogen bridge with the potential drug. So here we have halogen bridge will be able to be with the oxygen or with the nitrogen of the backbone, but mainly with the oxygen, and the side chain will be looking towards any other part. Conclusions for all this part of intermolecular interactions that I hope you review. Do not forget more, because now we are going to see them in abundance in several concrete. Then we are going to have that they are hydrogen bridge P, stacking halogen bridge to a lesser extent, the ionics, the hydrophobic, etc. Name me one that is not here. Here it is named the most relevant hydrogen bridge, halogen bridge P. Very well, for example, there it does not show hydrophobic. They are yes ionics, or Salini bridge also, because they do not mention the van der Waals. Exact, and all the drugs and all the surfaces have van der Waals, so it is not something in what one thinks to make drug design. It should be considered the angular element in the interactions of hydrogen bridge and of halogen bridge. Do not forget that the angle give the same and the distance neither. How was the distance of the hydrogen bridge? Already perfect, from 2 to 2.5 angstrom approximately, and the bridge of halogen exact, very well, from 3 to 4, and angle, and also distance, because one says the closer the better halogen bridge. If it is too close, what will happen? Hysterical repulsion. Prime the repulsion over the attraction in the case of the p-stacking interactions. When both rings are complementary in electronic density, that means this. Exact, if that is given, and usually in the drug. For the general in the drug, it is easier to have the ring as an electrophil, the aromatic ring as an electrophil. Because I usually say, because in the protein, that aromatic ring, tyrosine tryptophan, which are electro-enriched and knowledge-based on the residues of the site of interest and the states of ionization to physiological pH and amino acids. Have it in consideration for an appropriate design of new OK. There is only one case in which there may be an aromatic ring of the electrophilic protein, which with which residues, to see if they are remembering the measure that is appearing. Exactly, with histidina, very well. Then it may be that with histidina, it is that it is protonated, will act as an electrophilic aromatic ring, and there we would require that the drug is nucleophile.